Continuing our study of logs or logarithms, which is just sort of another way of showing exponents. And you guys studied a lot on exponents in middle school and in early senior school. And one of the things you learned in grade 9 was 3 exponent laws. That when we multiply 2 powers together, the base stays the same and we add the exponents. When we divide 2 powers with the same base, the base stays the same, we subtract the exponents. And when we take 1 power to another power, base stays the same and we multiply the exponents. Very similar, or similarly, there are 3 log laws that you should know. And for all of these, the base of the logs have to be the same. If I take the log of 2 things being multiplied together, that is the same as the log of the first thing plus the log of the second thing. Okay? You will be given these log laws. If I take the log of, or actually, sorry, I'll do an example. So as an example, we've got log base 6 of 9 plus log base 6 of 4. You could not do these separately because 6 to the what is 9. You can't do that in your head. I mean, you can do it, but you would need a calculator to do it. Okay? You can't do this in your head. However, when we add 2 logs together with the same base, that is the same as log base 6 of multiplying the 2 numbers. This log law, we can go from plus to multiplication, which is the same as the log base 6 of 36. Now remember how to evaluate a log. Think of it as an exponent. If we're trying to figure out log base 6 of 36, we're asking ourselves 6 to the what equals 36? 2. So notice when we put those together by the log laws, by multiplying, we could evaluate it in our head. For division, if we are taking the log of 2 things being divided, 2 expressions being divided, things, okay? That is the same as taking the log of the first expression, the top expression, minus the log of the bottom expression. Or vice versa. So if I see 2 logs being subtracted, I can change this to a single log of division. Base stays the same, but now I just divide the 2 numbers. And when I do that, I get log base 2 of 16, which I can do in my head. Remember, to evaluate a log, think of it like an exponent. This becomes the base. The answer is what I'm looking for, and the argument becomes the answer in the exponent. So 2 to the what is 16? 4. The final log law, which we call power of a power, is that if we take the log of an expression being raised to an exponent, that is the same as that exponent being multiplied by the log. So really all I'm doing is I'm taking the exponent and I'm putting it in front of the log and multiplying it. So as an example, whenever you see an exponent in a log, bring it in front. So this becomes 5 times the log of base 7 of 49. Well, what's the log base 7 of 49? In other words, 7 to the what is 49? So this becomes 2, so I get 5 times 2, which is 10. So we can use the log laws to help us evaluate logs that we'd normally have to use a calculator for. Okay. We can also use log laws to simplify expressions or expand expressions, which we're going to talk about now. What I want to do with questions like this is I've got a whole bunch of logs. I want to condense it to one log. First thing that we should do is look at any numbers in front, if there are any coefficients of the logs. In this case, there are. How do we get rid of this coefficient? Don't we make it the exponent? So this is the same as log base 9 of x squared plus log base 9 of y minus log base 9 of z. Why did I wanted to get rid of this 2 in front because now I can use my other log laws to combine. When I add 2 logs with the same base, that's the same as multiplying. When I subtract a log, that's the same as? So I'm going to multiply these 2 and divide this. So I'm going to make a single log base 9, multiply the x squared times y, but divide the z. Or think of it this way. When you're changing from a whole bunch of logs to a single one, if it's got a plus in front, it's going to be in the numerator of a fraction. This has got a plus in front, it's going to be in the numerator. This has got a minus in front, it's going to be in the denominator. That's another way you can think of it when we put logs together. So you want to move any coefficients first, and then use the other 2 log laws to make a single log expression. So for B, I've got a number in front here, I've got a number in front here, so I want to move them to exponents. So 1/2 times log base 3 of A is the same as log base 3 of A to the 1/2. All I'm doing is just moving it into the exponent into the log. Minus log base 3 of B to the 3rd. I wanted to clear out any numbers in front of the logs because now I can combine it into a single log. Base stays the same. What do I do when I subtract 2 logs and I want to make a single? Divide them. So it's the same as A to the 1/2 divide B to the 3rd. Or the way I told you before, this has got a plus in front, so it would be in the numerator. This has got a minus in front, it would be in the denominator. You could go a little further, but you don't have to. Because there is another way to say A to the 1/2. Nope, those are 2 different exponents. When you raise something to the 1/2, it's the same as taking the square root of it. You do not have to, like, this is correct and this is correct. Sometimes when we get fraction exponents, we change them to radicals in our final answer. But I'm perfectly fine accepting this. Okay. So remember, get rid of the coefficients in front and then combine into a single log. So this one here. Don't worry about this state restrictions yet. I'm not gonna cover that just yet. We'll do that when we do equations. So any exponents I see in front, I want to pull, or sorry, any coefficients I see in front, I want to pull as an exponent. That's the first thing I want to do. So I get log w squared. What's the base here, by the way? 10. Don't have to change the second one. Third one becomes log y to the 1/3. And the fourth one becomes log z to the 1/2. I wanted all those numbers out in front away because now I can combine it into a single. What goes in the numerator? Anything that has plus in front. W squared times z to the 1/2. Anything that has a minus in front is getting divided, so it goes in the denominator. So x down here times y to the 1/3. We could change the fraction exponents to radical form. You don't have to. So I would suggest just leave it like this. It'll be fine. For D, well, there's no coefficients in front, so I don't have to pull them into exponents. So all I do is like write a single log. What do I do with these two? When we go from addition to, what's that log law? Multiply. So what's x squared times x? That's it. Okay, so that's going from an expanded form to a single log. What happens if we go the other way? Well, do the steps in reverse. Expand it out using plus and minus, and then any exponents in the logs, pull them in front. Because isn't that what we did to go from expanded form to 1? We pulled all the numbers in front into exponents, and then we compressed it all into 1. Well, we're just doing the opposite. So for A, when I take the log of two expressions being divided, that's the same as writing it out as the log of the top expression minus the log of the bottom. Remember, subtraction goes to division, division goes to subtraction, depending on which order we're asked. Then any exponents you see in the logs have to be pulled in front to get the proper expanded form. So our final expanded form would look like this. Thank you. Yeah, base stays the same. For the second one, what is this as an exponent? Y to the 1/2. So you need to think about that when we spread it out, expand it. So log base A of X, well, because I'm timesing Y to the 1/2, that's the same as adding log base A Y to the 1/2. And I'm dividing Z, that is Z squared, isn't it? Yeah. When I'm dividing Z squared, when I expand it out, that's the same as subtracting log base A of Z squared. So I've expanded it out, and now any exponents in the logs have to be pulled in front for the expansion to be complete. So I get an answer of log base A of X plus 1/2 log base A of Y minus 2 times log base A of Z. And that is my final answer. So this is just getting used to you applying the log laws. And we need to know how to apply them because, again, the ultimate goal, like in so many units we've done, is how to go to equations. Because we use equations to solve all sorts of problems. For C, there's no base, so we assume it's 10. First thing I want to do, is expand it out. How many logs am I going to write when I expand it out? 3. Why 3? Because I've got a W to the third, I've got an X, and I've got this together. You don't do each one separately. That has to stay together. So anything up top has a positive in front. So log W cubed plus log X minus log, and in parentheses, Y minus 1. Is there anything I have to simplify further or expand further? The cube has, because there's an exponent, it has to be pulled in front. So I get 3W, 3W. 3 log W plus log X minus log Y minus 1. Okay, next example is kind of what we did at the beginning, how to evaluate log expressions by using the log laws to help us. Because four to the what is 32? I don't know, some decimal. 4 to the what is 2? Well, that's 1/2, but okay. But I can't do these separately in my head. However, if I've got 2 logs being added, that is the same as a single log of these 2 expressions being multiplied. And 32 times 2 is 64. So a simpler way to say that is log base 4 of 64. Now you're ready to answer it. Remember, how do you evaluate logs? 4 to the what is 64? 3. How could I write this as a single log? Times? Which is the same as log base 3 of 9. Which means 3 to the what is 9? 2. How could I write this as a single log? First of all, there's no base, so we assume that it's 10. Well, to write 4 plus 5, that's the, when I combine it, what do I do with the 4 and 5? Multiply them, so 4 times 5. And when I subtract log 2 and make it into a single log, that means divide 2. So that means I get log base 10 of 10 equals 1. 10 to the what equals 10? 1. This one, before I can create a single log, I've got numbers in front, so I got to put them as exponents. So I get log base 6 of 12 squared minus log base 6 of 16 to the 1/2. I'm subtracting, which means when I combine into a single log, I divide. So it's 12 squared divide, or the log base 6 of 12 squared divides 16 to the 1/2. Well, we can do these. What is 12 squared? What is 16 to the 1/2? Root 16, 4. And I can keep going. Oh, there shouldn't be an equal sign there. And I can keep going. 144 divide 4 gives me 36. So I've gone from this all the way down to this as an equivalent. And now I can actually evaluate it. 6 to the what is 36? So it equals 2. Okay, the last thing I want to talk about before we get into log equations, which we'll do next week with 8.4 and 8.5, is what happens, like all of these ones, we were able to change them and then do them in our head. What happens if we just can't do that? Besides giving up. Right? Here's what we can do. And this is called the change of base theorem. When we take the log of any base of something, remember this is the base, this is the argument, that's the same as the log of the argument divided by the log of the base. And remember on your calculator, your log only does base 10. Because if a log is by itself, you assume the base is 10. So I could change this base to anything I wanted to. Okay? So we're going to choose, We're going to change logs to a base of 10 so that we can use our calculator to evaluate. You just have to see the pattern here. So log base 2 of 3, that 2 to the what is 3? I can't do that in my head. But it does equal log base 10 of 3 divide log base 10 of 2. So this becomes the top log, this base becomes the bottom. And then the base changes to 10. Now is where you use your calculator. So you would simply do, and you should be familiar with how to do it, log, and it should open up a set of parentheses for you, 3 close parentheses divide log 2 close parentheses. What'd you guys get? 2 decimal places. 1.58. Okay? So you can see how we do these. Whenever you encounter one that you just can't do in your head, you can use the change of base theorem and use division to find the approximate answer. So this one, can't do this one in my head. So log base 10 of 785 divide log base 10 of 5. And when you do that, again, you should be doing this on your own calculator so you're familiar with how to do it and getting the correct answer. You should get 4.14. This next one, we're adding 2 logs. I can't combine them. Why can't I combine them? What's preventing me from making this a single log? Bases have to be the same. So what I got to do is I've got to evaluate each one separately. Log base 10 of 8 divide log base 10 of 3 plus log base 10 of 7 divide log base 10 of 4. And again, I'm going to need my calculator to do that. So log 8 divide log 3, because remember log base 10 and log mean the same thing. Log 8 divide log 3 gives me about 1.89. Log 7 divide log 4 gives me about 1.40. So when I add those two, I will get approximately 3.29. Okay, final one. Well, all the bases are the same, so I could combine these into a single log. So it's going to be log base 7. Well, this is positive, so the 6 goes up top. This is positive, so I'm timesing by 2 up top. This is negative in front, so I'm dividing by 3. So I get log base 7 of 12 divide 3, which is 4. 7 to the what is 4? I can't do that in my head. So this is where we've got to use the change of base, where we go log 4 divide log 7, and we will get our approximate answer. and log 4 divide log 7. Oops. You need parentheses, closing parentheses there on a lot of calculators. Otherwise, it'll mix up the order of operations. You'll get an incorrect answer. You should get approximately 0. We'll just go 2 again, 71. So log laws and change of base. We're sort of now ready to start solving exponential equations where we have to use logs and logarithmic equations themselves. And then we're going to see how we can use those in certain real life or real life problem situations. Okay.